So welcome to the first Astrobiology Journal Club of the new term. My name is Ben, and me and Sean Ford will be co-hosting this. I want to welcome everyone who's tuning in live on SegaNet. Today I'm going to be talking about a really interesting paper that came out this summer from an Italian group. It was published in Science in July, and it is on a detection of subglacial water in Mars's southern polar ice cap. So let me begin by just motivating why do we care about liquid water on Mars? And the easy answer is because there might be life there. But to go into more detail, we want to think about Mars's early history, and we know it was once a wet planet. Estimates are from about 4.5 to 3.5 billion years ago. It had likely an ocean or various oceans. And we know that Mars was a wet planet because we can see the dried up riverbeds, we can see the ancient shorelines, and we can see things like water saturated clays. And then you can think about how long it took Mars to lose its atmosphere, and you can kind of put an estimate on how long those oceans existed. So about 4.5 to 3.5 billion years ago. And we know that in that time, life actually, so we can maybe imagine this kind of picture of Mars. We know in that time that on Earth, life emerged between 4.5 and 3.5 billion years ago. This is a great graphic from a paper that Andrew, Ralph, Paul, and I wrote for Astrobiology, a review that just came out this year, where you can see that there's two boundaries that demarcate this time interval for the origin of life on Earth. You can see the astrophysical constraints in red, which show you that Earth probably became habitable between 4.5 and 3.9 billion years ago. And based on the evidence of biosignatures on the Earth, we know life existed likely by 3.7 billion years ago, which means that life emerged on Earth within about 200 to 800 million years. So, since Mars had a similar history as the early Earth, and it was wet for about a billion years, life could have definitely emerged on Mars as well. Not definitely, possibly. Finally, we know that there are similar places on the Earth, like the subsurface lakes, that are swarming with microbial life. Just ask this guy. Dale Anderson came to visit us 2 years ago and gave a colloquium on his scuba diving adventures in Lake Untersee in Antarctica, where he found microbial mats in extremely low light and cold conditions. And he found dozens of species of bacteria and archaea which were just thriving in these intense subsurface lakes in Antarctica. So what did this group find? Well, they found a 20-kilometer wide subglacial body of water, which is 1.5 kilometers underneath the surface. Just this box you see right here, Planum Australe, that's what they call this southern polar region. And you can see the coordinates there. That's where they took their radar measurements, which transitions into how did they detect this subsurface water? Well, they used radar. The instrument's called MARSIS, Mars Advanced Radar for Subsurface and Ionosphere Sounding, and it's aboard the Mars Express, which is a European Space Agency spacecraft satellite. It launched in 2003, so it's actually been around Mars for quite a while. And the readings that it took, the radar profiles, were collected between 2012 and 2015. So this is a pretty long program for detecting this subsurface material. But how does it work exactly? So I need to teach you a little bit about BASAL echoes. There's not a lot of physics in here, but there's some key conceptual parts. The first is when a radio wave, or rather any wave, any light wave, hits an interface, for instance, air-water, rock-water, solid water, liquid water, a portion of this wave will be reflected. And the intensity of the reflection that you get back tells you something about the interface, something about the material below the interface. Specifically, it tells you about the dielectric permittivity, this epsilon r you see here. Now, the dielectric permittivity, it's not entirely important what that is. I mean, it's generally how much a material can hold on to an internal electric field. But what it does tell you is how much radio waves will be reflected off of it. So if the material has a very high dielectric permittivity, it will reflect more radio waves. You'll get a more intense radar reading. This can be explained with the Fresnel equations. Many of you have probably heard of indices of refraction. These are related to the dielectric permittivity. And this simple equation here shows you that the reflection R is equal to the index of refraction of material 1 minus that of material 2 divided by them added together all to the power of 2. And we know the relation between index of refraction here and dielectric permittivity is what you see right here in the square root. Now there's also a mu term, that's a permeability, but we don't care about that term because water, rock, air, it's all about the same as a vacuum. So really it's this epsilon r that we're trying to measure for this material below the interface. Now I brought up this equation because it kind of easily shows you the exact measurement that they did and how they actually got information out of it. They know R because they transmit radio waves down into the surface and then they waited for the reflection. The first reflection came at the surface and then at the next interface, so the first interface is CO2 and then the ice deposit. They call it the south polar layer deposit. So it's like icy, dusty rock. Then the radio wave that's transmit goes through and then reflects off the next interface, which we would think would be the Martian regolith and the icy deposit on top. That's where it gets interesting. So here is the measurement. On the y-axis you have the travel time, which can be converted into a distance, a depth, because we know the speed of light. And a long track distance shows you just the kind of the area. This is 1d, but the area in which they took these readings. You can see there's a bright surface reflection here, and then this SPLD, that's the layered deposit, that dusty ice. And then you get this other bright reflection right here. Now to put into something a little bit more easy to read, we have it down here, the surface reflections in red, and then in blue, you have the next interface, the base of the layered deposit. And then look at this area right here. You can see this blue signal that's actually becoming more intense than the surface reflection. Now imagine that, it goes down 1.5 kilometers and reflects back more intensely than the radio wave reflected off of the surface. So that's pretty exciting. That already tells you that the dielectric permittivity of this area here, whatever that material is, must be higher than whatever it is on the opposite side of this bright reflection. So we know that it's probably different than that regular Martian regolith. So that's the first kind of hint you see there. This is just the same thing in 2D to show you the area that they took these radio measurements, and this triangle here is where that bright reflection is. And this is in decibels here, so it's about 2.5 decibels in this bright region. Okay. So how do we get the actual information that we know this is liquid water? Well, based on that equation that I showed you, the Fresnel equation, if you know the reflectivity, which you do, and you make a reasonable estimate for what the dielectric permittivity is of that icy, dusty layered deposit, then you can get the dielectric permittivity of whatever's underneath the interface in this shiny material. And then you can match that value with known values, for example, on Earth. So we know, for instance, the dielectric permittivity of 4 to 15 is dry terrestrial rocks on Earth. Anything above 15 is always generally related to liquid water or liquid water saturated rocks. Now, in previous estimates of the Martian regolith, it suggested that it's about, the dry regolith is about 7.5 to 8.5. That's just the Martian dirt. Regolith is just a fancy way to say that. And also, this method has been kind of tried and has been proven tried and true in Antarctica and Greenland to detect subsurface lakes. So they've pointed the radar down at the ice and then been able to find these values of dielectric permittivity that are above 15 and use that to indicate, yes, there is in fact a subsurface lake right here. For instance, Lake Wintersea. Okay, so they had to model the dielectric permittivity of the layered deposit above the shiny reflection, because that's how they can estimate what the actual dielectric permittivity is of that material below the interface. So here we have on the y-axis the power, and on the x we have the permittivity of the basal material, that stuff that's underneath the layer deposit. The model in blue that you see there is a dusty, 10% dust, 90% water ice model that is at 205 Kelvin at the base and goes up linearly from there. So it's one of their plausible models. If you take that model and you compare it to the average basal echo power that was measured by the radar detector, that's that black line here, we see they intersect at 24 for basal permittivity. So we know everything above 15 is indicative of liquid water or water-saturated rocks. So just using that model, you can tell, okay, it's likely that this is liquid water. But everything in this blue region here is a plausible, or possible, I should say, model. On the far left, you have pure water ice. So there's no dirt in it at all. And even if you have a model, which would be very unlikely, to have pure water ice on top of this shiny region, it would intersect here, which is about 17. So still above that 15 permittivity that tells you that you are liquid water. So this is pretty good evidence that that bright reflection is indeed a liquid water source of some kind. This is shown in a different way, two different distributions, outside the bright reflecting region and inside the bright reflecting region. You can see that the distribution of basal permittivities or outside the reflecting region is around 7.5, most likely, or most commonly 7.5. There's some below, some above, of course, because it's not just one uniform material. And that's what they estimated for the regolith, 7.5 to 8.5. So that makes a lot of sense that this outside the bright reflector is just Martian regolith underneath that icy deposit. However, inside the bright reflecting region, you get most of your values above 15. And you can tell that these are two different distributions here. Now there are still some values that are below 15. So if we look kind of closely at the actual reflection again, right here, it's not uniform, right? There's some really dark regions within this bright region. So it's, you shouldn't picture something like one just 20-kilometer wide subsurface lake. It's probably got a lot of rocks in there and probably frozen in some areas, which are creating these lower dielectric permittivities. However, there are still mostly high permittivities here, which are indicative of liquid water at some regions within that bright reflecting region. Okay, what about some other possibilities? Is there something else to explain this bright radar reflection? They thought about solid CO2. This wouldn't be that weird to have solid CO2 there because it's been measured before to have CO2 freeze out on top of the ice caps in about a layer 1 meter thick. And the thought is, well, what if this CO2 that's on the surface, or maybe it's solid CO2 underneath the icy layer deposit, what if that's causing this reflection? So they modeled that. Just to be sure, there's a lot to unpack here, but I just want to bring your attention to the right side to start, B and D. B and D are a layer of CO2 underneath the deposit. A and C are CO2 above the surface. It's just two different locations for the CO2. What we can see in D here is that the model at three different frequencies, they don't reach the actual measured echo power. So we can already exclude for whatever thickness of CO2 from 0.1 to 100 meters, you're not going to get the same measurement if you have that CO2 underneath the layer deposit. What about on top of the layer deposit? Well, you can see some lines overlapping here, so there is indeed a plausible model if you have CO2 on the surface. However, the entire pole has the same reflectivity, reflection coefficient rather, and you can see this line is only straight up to about 2 meters, and then the reflectivity changes. And these models are only overlapping with the he measured values above 2. So 2 is like right here. So it doesn't really work out there. I actually don't know why they did this, because you can see just by looking at this, that this red line, it doesn't increase in brightness here. It's more or less consistent. The surface reflection is more or less consistent throughout the entire polar deposit. So this is enough evidence that you don't have CO2 on top, reflecting really brightly, causing a higher echo power at the base. Okay, so that is all. Just end on the conclusions here. Radar measurements were used to detect subglacial liquid water in the south polar deposit on Mars. The source is 1.5 kilometers below the surface, and it's 20 kilometers wide, but it's not uniform, so there's liquid water in there. It's probably more likely liquid water, saturated rocks, intermixed with some frozen water in there as well to create less of a uniform signal. The water's probably at 205 Kelvin, so very cold. We're not sure if life could exist at those temperatures. However, extremophiles on Earth suggest that maybe indeed some could have undergone natural selection and eventually thrive under such extreme conditions. So the liquid water is probably staying liquid due to perchlorates, magnesium and calcium perchlorates. And because there's liquid water, as we see here, permanent liquid water, at least while we're looking at it, if life did indeed emerge on Mars 4.5, 3.5 billion years ago, then it's possible that it could be inhabiting this location. And when humans go to Mars to explore, this polar region is definitely going to be a high priority region of interest. There's going to be a lot of planetary protection, hoops to jump through to even go there, but it's definitely probably the most interesting region on Mars after this paper came out.